Hello everyone. Today we're in tutorial 5, first year university physics, energy and power. Okay, let's go to my notes. Tutorial 5, energy and power. I'm going to read this out to you first and then go to the whiteboard to explain things in more detail. Number 1, work equals force times distance, and in words. The force acts in a direction of motion. It's important that you understand this. In this formula, this force must be in the direction of the motion to get the correct work. In number 2, we think of a force which is applied at an angle theta to the horizontal. As in many problems, it's always good to resolve a vector horizontally and vertically. So, as I've always said, when you're resolving vectors, make the vector the diagonal of a rectangle. The two sides will then be the components. All the tails are tied together, and all the vectors point away from their tails. So this is a way of judging the directions of the components. So here, this is the adjacent. So without having to write down the formula for cos theta as adjacent of a hypotenuse, it's the adjacent, so you know it's going to be cos multiplied by the hypotenuse. F is the magnitude of the vector F. I've only written magnitudes here. So it's F cos theta, and the vertical is F sin theta. In this, we're assuming F sin theta is not big enough to lift the object. In this case, the only force that does work is the force in the direction of motion, which is F cos theta. So work in the x direction is F cos theta multiplied by x. But in the y direction, it doesn't move. So the work done is 0. This force, however, will affect the value of gravity. But that's not relevant for in calculating the work that's being done. So the important point here, a force perpendicular to the direction of motion does no work. So a satellite that rotates around the Earth, gravitational force is perpendicular to the satellite's orbit at every point. So no work is done by gravity as the satellite rotates around the Earth. This is because of this, what we have just said here. Power is defined as a rate of doing work, work divided by time. Since energy and work are essentially equivalent, they may have different interpretations in certain places, but they have the same units, and they're obviously related. So we can also define power as energy over time, and two alternative definitions. Another formula that is very useful and can be easily proved from the definition of power is equal work over time. Since work is force times distance, we can substitute. And S, the distance divided by time, is the velocity. So we have this other very useful formula for power. So let me go to the whiteboard and emphasize these ideas. Expand the whiteboard. Okay. So let's start with my definition of work. Work equals force times distance, the force being in the direction of motion. Now when we have a force, acting at an angle to the horizontal, angle theta. As we have said, I resolve the force into horizontal and vertical components. So I resolve by drawing a rectangle. You can draw a triangle, but it's often easier and more convenient to draw a rectangle instead. And my components are the two sides of the rectangle. You can see if I move this to here, I've got the equivalent thing with a triangle. So this is my Fy components. This is my Fx component, which is This is the magnitude here is F. It's F cos theta equals F sine theta. And as we have said, since there's no movement in the y direction, we've assumed this force is not big enough to lift it, otherwise work will be done. So we assume that Fy is not big enough to lift the object from the horizontal, not a very good horizontal. So we have the work done then is purely due to the horizontal force. Fx dot theta equals not theta. Dot x equals F cos theta dot x. Maybe I should write it like that. Dot means multiplication. This is the work in the x direction. I can put x if you want. Work in the y direction. Fy dot y. F sine theta. But y is equal to 0. So the work done then is 0, as we have said. So forces perpendicular to the direction of motion do no work. My definition of power is the rate of doing work, so it's work over time, or power equals energy over time. Now from this, I can get a nice alternative formula which is useful in a number of cases. So P equals work over time. Work is force times distance. I often like to use S as distance as opposed to X or Y. This is distance over time. So we have my formula, force times velocity. This is another very useful formula. So let's emphasize it. Okay, let's go to the next page of my notes. The work energy theorem. The work energy theorem states that the work done by a net force is equal to the change in kinetic energy. Mathematically, we write it like this. Force times distance, the net force times distance, equals the change of kinetic energy. And this is called the work energy theorem. I put magnitude signs here because the final velocity may be less than the initial velocity. If the force is in the direction opposite to the motion, it will slow the object down. So the final velocity will be less than the initial velocity. So this quantity will be negative. But in doing this calculation, we want always to have a positive quantity. So we put magnitude signs, meaning that when we do the calculation, we take the positive value. If the force is in the direction of motion, then my velocity will increase, and as you would expect. And this is what this thing says here. The thing to note with the work energy theorem is that it's general. It works in a variety of cases. For example, it's going to work in the horizontal direction. It will also work on a slope. It works when friction is present, for example, when there's friction on the slope or friction on the ground. It also works when external forces are acting. So my work energy theorem is general and it saves a lot of calculation. You can normally do the same calculation by first principle, which is much longer. But if you remember this principle, it saves calculation. So this is my important work energy theorem. Let me make sure that you all have the notes on the screen. Right. The next page, potential energy. Again, let me read through this page and then explain some of the ideas on the whiteboard. Potential energy is defined as the capacity to do work. it can also be thought of as stored work. So if we, for example, and by the way, we can define the zero of energy anywhere we want, and then calculate from that reference point. The reason is that physically, it is only energy differences that have physical significance. So the absolute value of energy doesn't actually have any physical effect. So it's differences in energy which have physical significance. So in doing various problems, it's sometimes convenient to define the zero of the potential energy somewhere other than the ground. Mostly we'll choose the ground. But keep in mind, we have a freedom to choose our zero of potential energy. Once you've chosen this zero, if I start with the object here and push it up here, I get an energy mgh. I'm going to explain this in more detail on the whiteboard. This formula comes from work equals force times distance. Potential energy is basically stored work. So my W can be written as PE. My F, the force producing, or the force that we have to do work against to raise it, is mg. So this is the work done, is mg, and the distance is h. As I've said, the zero of energy can be chosen anywhere, since only differences in energy have physical significance. For potential energy, the zero is usually chosen to be ground level, but not always. Notice that raising an object doing work against gravity increases its potential energy, while lowering an object, work is done, reduces its potential energy. Final point, gravitational force, I should maybe put an AL there. Gravitational force is a conservative force, meaning that work done is independent of path. Thus, the potential energy between 2 points is the same no matter how the object moves between the points. So if I take a point A and B, let me explain this on the next page in more detail. I mean on the whiteboard. All right, let's look at the idea of potential energy then. Potential energy is the capacity to do work, or alternatively, can be thought of as stored work. So let me define my potential energy at this height to be 0. This is y equals 0. Let me raise it to a height h, y equals h. And here I have a certain amount of potential energy. I'll do the formula for you in a minute. Now the point is this. If I take an object from here, in order to lift it, I have to do work against gravity. Gravity is pointing downwards, mg, so I must do work against gravity to lift it to here. So all of that work done can be thought of as stored energy. Or you can think of this as the capacity or potential to do work. For example, supposing we have water in a well. So there's a bucket. Now what I can do is I can use a system of weights. Let me draw a big circle. My diagram is not fantastic. If that's the ground level, let me put a weight there. My diagram is not to scale, but the point is this. To lower the bucket, I have to lift the weight up. The scale is completely wrong. I have to lift the weight up. But now, if I want to bring the bucket back up again, I release the weight from here, and the gravity pulls it down to the ground. As it pulls it down to the ground, the bucket lifts up. Obviously, I need to put the pulley much higher in order to get it to the top. My diagram is not very good to scale. But you can see that this is now doing work as it goes down. So this is in this sense that we think of potential energy as the capacity to do work. Now, as for the formula comes from force times distance. This is the force I'm doing work against, or this is the force that's doing work if I allow it to fall. Either way, we're either storing the energy or we're releasing this energy. But whichever way we're doing it, this work is equal to force times distance. The force is the force due to gravity, which is mg. The distance is h, and I get my formula, mgh. The work, once we put it up here, is stored energy. So the work is now potential energy. And we get my formula, mgh. Okay, let me clear that and go to the fact that gravitational energy is conservative. Gravitational force is conservative. Let me first of all give you the general definition of a conservative force. If I have a force field and I've got 2 points A and B, and I ask for the work done between these 2 points, if I go in a straight line, I've got force times distance, call that S. Let me say I use a force F due to the field. Sorry. Work equals force times distance. Now the point is this, that if I go from A to B by this other path, the work done is exactly the same. Or if I go like this, the work done is the same. So when the work done between 2 points is completely independent of the path, then we say the force is conservative. My spelling here went astray. Let me correct that. Conservative. So when we look specifically, and this is true for any conservative force, but if I look at specifically the gravitational force, it works between the same heights, no matter how you get to the same height. So instead of thinking of points, let's think of heights. If this is my ground level, my PE is 0. This is PE equals mgh. So this one I go from here to here. Let me put an arrow there if you want. This is height h. Now the thing is this. If I go from one height to another height by any path, then the work, the potential energy, is mgh. It can be any path. Let me do one more. A, B. The same heights rather than the same points. A line is not very good. But again, I can take any path I want. And my potential energy will be mgh. Okay. This is very important doing calculations because you trying to calculate these things in terms of forces will be extremely complicated and really will be very, in cases like this, it is so difficult. But using conservation of energy and remembering this, you can solve quite a few problems. But we'll come to examples in your tutorial sheet. Let me go back to my notes. This is basically, yes, conservation of energy. But first, kinetic energy. Basically, we said the potential energy is stored energy. Now, kinetic energy is energy by reason of motion. The kinetic energy of a body, so that B should be a D, is the energy of a body has by reason of its motion. So this is energy possessed by a body because it is moving. And it's given by a formula you all know, a half mv squared. Now we come to the important subject of conservation of mechanical energy. Remember, there are many forms of energy. There's mechanical energy, there's electromagnetic energy, electrostatic energy. And when you talk about chemical energy, you're essentially talking of electromagnetic energy. There's nuclear energy. From Einstein's relation, E equals mc squared. Now, energy is generally conserved, but if you're looking at a system involving many kinds of energy, then you have to take account of all the different kinds of energy. Here we're focused purely on mechanical energy, which is either potential energy or kinetic energy. The potential energy may be due to many bodies, not just a single body. Similar with kinetic energy, may be due to many bodies. So you're looking at the entire system. So when you look at the entire system, the total energy in that system is conserved. So the mechanical energy, which is equal to the total potential energy plus the total kinetic energy, is equal to a constant. And using my formulas, this applies for a single body. When I've got more than one body, I have to do mgh for all of them and a half mv squared for all of them. So mgh plus a half mv squared equals constant. Now for this relationship to be true, we must have that the change in potential energy must equal the change in kinetic energy. So if the kinetic energy goes up, the total kinetic energy goes up, the potential energy must go down. Similarly, if the potential energy increases, the kinetic energy must decrease. We have put the subscript total since the change in kinetic and potential energies may be due to more than one object, as we have said. Equation 2 is perhaps more useful for calculations. When we do calculations, it will be this form that's more useful than this one. But it depends on the problem. But generally speaking, this will be the more useful one. In words, equation 2 states that we're neglecting friction here. If kinetic energy is lost, the same amount of potential energy is gained, and vice versa. In equation 2, energy lost is indicated with a minus sign, while energy gained is indicated with a positive sign. So we can write equation 2 as energy lost plus energy gained. You see, we don't know whether it's kinetic or potential that's lost, so we'll write it generally as energy lost, and similarly here. So I have a minus attached to energy lost and a plus attached to energy gained. So I can write my equation like this. Now, if friction is present, then the frictional force is added. And the reason it's added is this. When we lose energy, energy needs to be conserved. So when we lose energy, where does the energy go? Well, if I lose energy, something else gains energy. And when friction is present, some of this energy that's lost goes into the friction. So this is why we have to add it. So the sum of these two things must equal the energy lost, which is what I've written there. Now this is an important point. I think many of you in your lectures write your equation like this, equal to 0. And then you make the energy loss negative and the energy gain positive and the work done by friction positive. But what I like to do is a simple algebraic thing. Let's take the energy loss across the equal sign. So I take it across the equal sign, and the minus, by the rules of algebra, becomes a plus. And then all I've done here is to write the equation the other way around. So energy lost equals energy gained plus the work done by friction. In this case, you always make sure the quantities are positive. So you always arrange, for example, if you've gained potential energy, you put the largest value first, mgh2 minus mgh1, where h2 is bigger than h1, so you make it positive. Similarly, if you've gained kinetic energy, a half mvf squared minus a half mvi squared, you put the bigger kinetic energy first in the calculation. Alternatively, if you want, you put magnitude signs. Either way, you must arrange that the energy loss is given a plus sign, energy gained is given a plus sign, work done by friction is given a plus sign. In calculating for each object in the system, you calculate the change in kinetic energy by this formula. I put magnitude signs in because the final velocity may be less than the initial velocity. When kinetic energy is lost, the final velocity will be less than the initial velocity. If kinetic energy increases, then the Vf will be bigger than Vi, so this will come out positive anyway. For potential energy, similarly, Hf may be less than Hi, so this will become negative, but I need to use the positive value. Finally, when an external force is present, in many of your problems, you're not going to have an external force, but I think I've seen some problems in your tutorials with an external force. But in any case, if it is present, then the formula becomes this. Energy lost plus the work done by the external force is equal to energy gained plus work done by friction. Many of the problems you're going to come across are going to be either this involving friction or even problems which don't involve friction at all. So it's this form that we're going to use the most. But in case you come slightly more difficult problems, keep this one in mind. I'll finally finish with the units of energy. The SI unit of energy is called the joule, named after James Prescott Joule, and is denoted by the symbol capital J. So this is my joule. Now, it's quite nice to know your units. These are derived units, by the way, because they can be written in terms of the base SI units. So it's nice to write your derived unit in terms of its base SI units, at least to be aware of how you can do it. And we can do this by using the formula for work equals force times distance. So let's see how we can get the units then. Work equals force times distance. Force, by Newton's second law, is mass times acceleration. Acceleration, by definition, is velocity over time. So I get mvt over d. Let me shift the t under the d, and then I write my velocity in brackets as distance over time. So you can see I've got d squared over t squared. So mass is measured in kilograms in base SI units. D is measured in meters, and S is measured in seconds. This is divided, so this should be -2 here. That's very naughty. This must be a -2, it's t squared, so let me write this on the whiteboard. So we've got my unit then for energy, capital J. By the way, the name of a unit is always written with a small initial letter. In other words, they're not capitalized. Even though this is the name of a person, or the unit is named after the name of a person, it's never capitalized. Similarly with the Newton, it's a capital N, but we write the Newton in small letters, even though it's named after Isaac Newton. So that's my unit. Now, in terms of base SI units, we have work equals force times distance. Force is mass times acceleration. Acceleration is velocity over time. Let me take the t outside. So I get d over t. Velocity is distance over time. So I have work is equal to mass multiplied by distance squared divided by time squared. So when I write my SI units down, 1 joule equals, mass is measured in kilograms, distance in meters, so that's meters squared, and then time is seconds, so it's seconds squared. So this is my energy in terms of the base, my unit of energy in terms of base SI units. I often like to write, instead of writing it like this, you can do it the way you wish. I like to write it as s to the minus 2. Another way of writing it, let me write all the possibilities. I'm not fond of this way of writing because sometimes you're dividing by more than one unit. So this is the 3 ways you can write your energy in terms of base SI units. It's not too straight. So let's go back to the whiteboard, to my notes. Okay, so this must be a 2, so I emphasize that. It's a mistake. Notice that the name of the unit is never capitalized, even when it is named after a scientist. Now the SI unit of power, it's called the watt, and again, it's named after James Watt. The symbol is capital W, but it's written as a lowercase watt. We can express this also in terms of base SI units, again by using the formula. Since power is energy over time, then we can take the unit of joules, as kilograms meters, s to the minus 2, divided by an extra time, so it becomes kilograms meters squared, s to the power minus 3. So I can get my watts in terms of my base SI units. Now another unit of power that you may find you'll come across, this comes from the British imperial system of units, and it's called the horsepower. Frankly, British imperial units, which are also used in UK and America, perhaps more in America now, it's not really a very convenient way. You've got feet and inches, you've got 12 inches in a foot, and so on, 3 feet in a yard. They really aren't convenient units. Nevertheless, the horsepower is used, and its relationship to the watt is that 1 horsepower is equal to 746 watts. You may come across this in your tutorial questions. Okay, that concludes our revision notes on energy. Okay, let me say bye-bye for now, and I'll see you at the next tutorial.